Hello and good evening. I did not expect to be doing this recording today, but good news. Senior round 2 was not too bad, and so I decided that I might as well get the solutions out this evening. So if you're watching this on the evening of the senior round 2 itself, I hope it went well for you. If you're watching it the day after, I also hope it went well for you, of course, but maybe the experience is a little bit less fresh in your mind. In any case, this was not a very difficult senior round 2 paper objectively. That's not a bad thing, especially if you're comparing it to 2023 and 2022. It is probably going to be impossible to predict the difficulty of the next couple of years of the senior round 2 since the difficulty has swung pretty dramatically. So in any case, it's a good reminder that we should be just solving the questions in front of us. It's all fun and sometimes pretty entertaining to joke about cutoffs being at one point 2 upon 50 and at the other point 32 upon 50, but well, whatever it may be, we just solve the question in front of us. Now the questions in front of us are not too bad. I mean, they can be considered to be objectively interesting questions, just that maybe as a collective for senior, they are an unusually easy set of 5 questions, but we can still learn some stuff from it. And so without further ado, let's jump into the geometry question 1. The geometry question is not that hard to draw, first of all, because it gets to the point quite quickly. You have an acute triangle. And then put D on BC such that AD equals to AB. So essentially you have just got an isosceles triangle that is extended a little bit out to C in some sense. Now you then draw 2 circles through C. The first circle, omega 1, is tangent at D to AD. The second circle is tangent to AB at B. And remember that we can read the rest of the question to save us a bit of time. We are also supposed to have it intersect on AC. So I can kind of suspect that this should be where the intersection is. And BFC, so that means that the circle apparently is something like this. Okay. Obviously, the diagram can be adjusted a little bit if we like. The important things that we want to note are definitely going to be the tangents, as well as the fact that these are equal. And so this turns out to be really straightforward because I want F to lie on AC, but the line FC is just the radical axis of the 2 circles. Now, the radical axis, in the case of 2 circles that do intersect, just refers to the line that is passing through their 2 intersections. The line, not just the line segment. The radical axis is called the radical axis because it is perpendicular to the line that is connecting the 2 radii. So that's the radius, and 2 radii, radical axis are perpendicular. Its definition is actually the set of points with equal power with respect to both circles. Now, the power refers to the power of a point in your, let's say, your tangent secant theorem, your intersecting secants, intersecting chords, right? The product of the 2 distances. Now, that basically means that we are immediately done because the power of, and this is how we write it, the power of A with respect to omega 1 is AB squared. And the power of A with respect to omega 2, oh, I'm writing the wrong one, right? It's actually AD squared, although they are the same thing. So let me just, omega 1 is the green circle. So AD squared, there's a tangent. omega 2, it's AB squared, and these are the same. That means that A lies on the radical axis. And that's it. It just means that AFC are collinear. Right? A lies on the radical axis FC, meaning the line. And so F lies on AC is also going to be true. This is not very hard. It is, however, a specific tool, right? So circle geometry, one of the important tools is being aware of this radical axis. If you are not aware of it, it's a bit difficult to show this, because even though it does make sense that AF times AC would be equal to both of these, the fact that the set of points is aligned is something that is non-trivial. Right? The fact that things on this line would have equal power is obvious, but the fact that it is just a line, you would have needed to know this in advance to give yourself a good chance of figuring it out. So hopefully, for those of you who solved it, I'm sure you know it. If you did not, now you know. The second question is common to junior. This is the junior Q5. Now, in order that this video be kept a bit shorter, I will not go through this question 5 again. I will just in the description below, I will just include a link to the junior video that I went through all the 5 questions of junior, and I'll just put a timestamp to when I go through question 5. So you can refer to that video. Of course, if let's say you've already seen that video, then you already know that essentially this is going to reduce down to a difference of squares. So let's jump past that and go on to question 3. So find the smallest positive integer n for which there exist integers x1, x2 up to xn, such that every integer from 1000 to 2000 can be written as a sum of the integers from x1 to xn without repetition. So this is a 2-part question. You're supposed to give me n, show me how to select the n numbers, as well as to show me why we cannot do it with even fewer. Now, I think it is quite easy to get to around the correct answer, right, to the vague vicinity, because we know that with n numbers, that there are only going to be 2 to the n, well, I guess we want non-empty, so non-empty subsets. And so it means that you have got at most 2 to the n minus 1 sums. Right? They may not be distinct, so maybe I should say at most 2 to the n minus 1 distinct sums. You will have 2 to the n minus 1 things to add up, but they may not be distinct. And so that means that your initial bound would be that 2 to the n minus 1 needs to be at least your 1001 possibilities. So n is at least 10. So this is on one end. The other end is that the construction is continuing on this powers of 2 trend. The construction is just going to be your powers of 2. Sort of like how many of you are familiar with the binary number system. Now, if you go up to 1024, which is 2 to the 10, now this will clearly work because you can write every number using its binary representation. In fact, not just from 1000 to 2000, but in fact from 1 to 2 to the 11 minus 1 can be expressed as such a sum. So this would mean that n equals to 11 is sufficient. which leaves us with the main n equals to 10 case itself. And so the main case of n equals to 10 is what we are concerned with. We are trying to, as simply as possible, either find a way to do it with 10 or find a way to explain why 10 does not work. Now we know that with n equals to 10, we are actually going to have 2 to the n minus 1, which is 1023 non-empty subsets. So I want to be able to get to everything from 1000 to 2000, which means that I have got 1001 values to try to hit using 1023 numbers. That feels pretty difficult. It feels pretty difficult because I feel like if I come up with anything, I'm going to almost certainly miss certain values because I'm also going to have some repeated values. It feels that way. Or some useless values, right? For example, in my construction on top 1, 2, 4, all of these small numbers add up to small numbers. They're not even going to reach 1000. And so therefore, it does feel like as if it should be not possible to do it with 10. I just need to look for some wastage that cannot be avoided. I mean, there will be different ways in which you can explain it. There'll be different ways in which you can explain it, but we just have to find the simplest one. So I've said about the small numbers. My argument is going to be that I need some small numbers. Because if there are too many big, so intuition, too many big is bad. And too many small is also bad. This feels extremely obvious. That's often the initial intuition for combi problems. Right? We just use the most straightforward, obvious intuition. Let me give you one example, but there are many ways in which you can do this. Right? So my suggestion is something like this. Now, if let's say that the sum of a few numbers is already past 2000. Let's say, for example, if the two biggest numbers, x9 plus x10 is more than 2000, then all the different things that you add in front of it will also be wasted, right? So plus x1 plus x2 plus x3 plus x1 plus x2 plus x3, anything will all be useless. So I only can afford to lose 22. And so I can just use some rough bound, like let's say that if my last, let's use 4 numbers. Why 4 numbers? Because you'll see in a moment it just fits well. If the last 4 numbers add up to more than 2000, then all the subsets, sorry, not the subsets, the supersets. So supersets of, not the sum of these 4 things have too big a sum. And the number of supersets, well, excluding itself. So let me say proper supersets. There will be 2 to the 6 minus 1 because there are 6 other things. So this sums that are above 2000, which is not possible. We only can afford 22. And so therefore, it means that this is smaller than 2000. And if this is smaller than 2000, it means that the x7, which is the smallest of these, is quite small, and everything else in front of it is even smaller. Smallest of these, it is going to be less than 500. So all of the first 7 numbers are less than 500. So the first thing I was saying is about too many big. So if the stuff behind add to too big, I have a problem. Now the stuff in front, now I have a lot of small ones. The new problem is that then all the numbers themselves and any pair of them sum to less than 1000. So any pair of them, yeah, so there are at least 7 plus 7 choose 2, which is 28 sums above 2000, which, sorry, not above 2000, that was just now was above 2000, now it's below 1000. Also it fails. So the conclusion is very simple. If I have too many big ones, I fail. I have too many small ones, I fail. So therefore, I fail regardless with the attempted n equals to 10. Right? So that means that n equals to 10 is not possible. And this shows that, again, your n is 11 is optimal. We have already shown that it works. This is showing that it is optimal. So that was not a very difficult combi question. It is sort of the typical idea of pigeonhole, except that we are just dealing with the fact that if I only have a little bit to spare, I still have a problem. Now, question 4 is a repeated problem from long time ago. Long time ago is when I was a student, so therefore that makes me old. This was an Open 2010 Q5. I do not know why the question is being repeated. At least it's a bit less egregious than what happened for Open 2023 and 2022. This is at least repeated from something that is almost 15 years ago, but nonetheless, it is true that some of you may have had an advantage and some of you may have not gotten the advantage of seeing this before. Yes, the good news is that unlike the open question that repeated in 2022 and 2023, this one is, I feel, very reasonable to figure out by yourself in comparison to that, even at the senior level and even with, especially because the other questions are not that time consuming, you would have time to work this out properly. Okay, so suppose p is a prime number and x, y, z are integers from between 0 and p, distinct integers sorted in order. If x cubed, y cubed, and z cubed have equal remainders when divided by p, prove that x squared plus y squared plus z squared is divisible by x plus y plus z. Okay, I'll just start by mentioning something just for those of you who are familiar. You can actually show that this would imply that P is 1 mod 3 and that x, y, z will just look like let's use a omega and a omega squared mod p, where omega is the third root of unity. You would show this using primitive roots, and the implication of this is that the x plus y plus z, this would actually be 0 because 1 plus omega squared, I should add the word primitive, third root of unity, 1 plus omega squared would be 0 mod p. So this would give you the conclusion that we're going to build up to in a slightly different way, just by low-powered tools, right? But if you are familiar with primitive roots, you would be able to get this conclusion in just like 3 lines. Now, I'll use the straightforward approach. This is admittedly quite similar to the suggested solution back from that Open 2010 problem, and I would not be surprised if the intended solution this year was exactly the same as it was intended to be 14 years ago. Let's start with x cubed is congruent to y cubed mod p, means that p divides the difference of cubes, which can be factored like this. Now, whenever you have a prime number divide something, we like to factorize that thing, because it means that if p divides ab, p divides a, or p divides b. This is actually the general definition of a prime number. The definition of prime in general is not that it only has a divisor of 1 in itself. It's just that it happens in integers, those mean the same thing. In other, let's just call them sets for now, there is a different meaning of prime, which is that p divides one or the other. It can't be the first one because of the size issue. Y minus x is also going to be strictly between 0 and p. Likewise, I can write the other two things down by symmetry. This makes sense to consider because it at least has something to do with x squared, y squared, and z squared. Now I continue on, I'm just going to subtract these because I would like to simplify it down a bit more, and I can see some cancellation will happen. So p divides, let's say, this difference between this and this, which is xz plus z squared minus xy minus y squared, and I can see a factorization is quite readily available to me. So after this work, I get that since this difference once again is between 0 and p, x plus y plus z is actually 0 mod p. It's divisible by p, which is the thing that I highlighted just now here, using the high-powered tool of primitive roots. Here, not a high-powered tool, only just basic algebraic identities. Next up is to use this, right? Whether you did this or you did the primitive roots approach, you still need to know what to do with this. And so it is quite useful to sometimes just take a pause and ask, is this easy to satisfy or not? The answer is no. This is not at all easy to satisfy because of the fact that x, y, z are so bounded. We only have got x plus y plus z can be p or 2p. So my main concern is going to be to make sure that x squared plus y squared plus z squared is divisible by p. The 2 is not an issue, right? Because if x plus y plus z is even, then all the x, y, and z's will have the same parity as their squares. So the sum of squares will also be even. So I'm not concerned about the 2. I just need to show x squared plus y squared plus z squared is also 0 mod p. Once more, if you actually wanted to show this, you can come back to here. So this would have implied also that if you had the primitive roots approach, this would also have been 0 mod p. So in fact, the primitive roots approach would almost instantly resolve it. Well, we shall just go with the low-powered approach a second time. The low-powered approach is that I already know x squared plus y squared plus z squared mod p is what I want. I see some stuff to do with it, so I'm just going to add all this together. The three things we had just now. I add everything this time because I want it to be symmetric. I want x squared, y squared, and z squared to all appear the same number of times. So they all appear 2 times. And of course, if they all appear 2 times, that's this extra xy plus xz plus yz that I want to get rid of. How I can get rid of that is simply by the fact that p would also divide x plus y plus z squared. Now that will give you 2 of the other one. You want to eliminate this in order to find that p divides the sum of squares, and therefore I just eliminate it by multiplying 2 times of the first one, sorry, multiplying 2 to the first one and subtracting off the second one. Which gives me 3 x squared plus y squared plus z squared. So that means p divides x squared plus y squared plus z squared, or p divides 3. Can p be 3? Last I checked, there are not 3 numbers between 0 and 3, so I don't have to worry about 3 at all. And therefore we are done. Now, I want to say that this is not a very difficult question in terms of modular arithmetic, but back in the day as a student, I don't think I solved it when it was in this open round 2 Q5. I don't think I solved it then. So it's not simple per se, but in terms of what you have to do here, if you know a lot of number theory, there is a simple way to do it. If you know very little number theory, there's also still a relatively simple way to do it. So that's what makes a question to me not so hard. There is a pair of viable options where you could go in either way. Now question 5, there is one more viable option. So there is a high-powered way, there is a low-powered way, and there is a I have seen the SMO Open 2020 round 1. Someone's going to ask me in the comments, why are there so many things to do with Open this year? Like the senior round 1 feels like an open paper, and then now the round 2 they took 2 questions from Open. I don't know. I have no input into how the round 2 is determined. But this, if you have taken the Open before, you will find it to be very familiar. In the SMO Open for that year, it gave this suggestion as a hint. There was a hint in the question from that Open paper, which was that you should let Cn equals to 1 over An plus 1 minus 1 half. This was the hint that they gave. Now the hint will work here. So method 1 to solve this question is you have seen that question before and you immediately remembered the substitution and you use the substitution. If you did, then you have been rewarded for your hard work. Congratulations, and that is fine. Now, an interesting thought to have is also about the fact that this would look like the tangent identity. Right, but the tangent identity is something plus something over 1 minus something times something. So this is not that. This is plus and plus. Well, what you could do is to actually do a substitution of An equals to Bn times I, where I is your imaginary number, square root of negative 1, and then that would allow you to, well, you have a common factor of I that will cancel out, but you would now have bk plus bn over 1 minus bk bn. So, and this would be 1 minus bn b out. So if you did this, you still need to know a bit more, because you want to let bn be tangent theta n. You need to understand what does tangent mean in imaginary numbers, right? Because bn is a pure imaginary number. What does tangent being imaginary mean? And so there is actually a meaning for it, which comes from the fact that if e to the I theta is cos theta plus I sine theta, it would mean that the definition of cosine is actually this for complex numbers. So it's e to the I theta minus e to the negative I theta over 2i. And then tangent would be the quotient. So this would be what you could do if you are familiar with your complex numbers. Now this is going to be interesting to think about if you're familiar, but if you are not familiar with this, we'll do something else. Now the bottom line is that this AK, this AN, is something like the hyperbolic tangent function. Exactly how is it like? Let's not worry about that, because I have not checked exactly how it is like that. But this would be actually similar to the sum identity of the tangent hyperbolic function, and the tangent hyperbolic function is very similar to the normal tangent function applied to imaginary numbers. Now that's the high-powered motivation behind this. I'm going to do something a lot more low-powered, which is just going to be a bahal of algebra. You should not consider it beneath you to do a pile of algebra, because in recent years, the SMO senior round 2 has been going in two directions. Very hard, so that even one question is very good. Then you should not feel bad to grind a lot of algebra. Or like this year, not so bad. Now, if it's not so bad, it is possible that we could say 4 hours is actually a healthy amount of time to allow you to try all the questions, including pile of algebra. So we're going to do pile of algebra here, and just, well, you'll see. The objective of the pile of algebra is also to justify that this hint is not needed. Because when I saw this question myself, I was a bit annoyed, because I know that I had seen that question before recently and there was a hint. So it felt a bit unfair, and I wanted to see if I was able to figure it out for myself. I mean, I already know what the hint says, so it gives me a bit of a clue, but let's see and follow. So I want to work on both sides in a way that it can be simplified. And the first step is that I'm going to just flip it over. And then I will add this to the top, because that will allow me to factorize the top. So this is adding 1 to both sides. The top is now factorizable. I'm going to combine steps, which is that I will factorize the top and I'll flip it back over again. Okay, so this was actually the form that was given in the open round 1 question. So they didn't give exactly the problem statement, they gave this. So this first few lines is basically, if nothing else, telling you that this is the same as that open round 1 question. Of course, that doesn't mean we are done. Back when I was trying to do the open round 1 question, I was hoping that I could do some partial fraction decomposition with this. but I was not very successful. And so, of course, there was a hint there. So I just followed the hint when I was trying out that problem. Now let's ignore the hint because in this question it was not there and try to rediscover that ourselves. Right? So the first 3 lines here is getting to that open round 1 problem. Now, I'm going to do a substitution first to let bi be 1 plus ai. I just replace the denominator by what I want to just be bk, bn, bm, bl, and when the denominator is like that, it's easier to simplify. So let's just write on the left side, the new situation is that I have got this. And the next thing I want to do is just to divide through. Now, remember the AK and all the other A started off as positive. The question I want to show is that they are bounded on both sides by B and C. So I need to show a lower and upper bound exist. So I'm going to keep track of bounds. Right? So this is now going to be, for now, the range is 1 to infinity. Plus 1. Okay, so that means that the division is fine, and I can also just divide through. And once I see this, I say, you know what? I would like to get rid of all of them from denominator since they are, well, all in the denominator right now. So I'm going to let Ci be 1 over Bi. So now I have got Cn plus Ck minus 2 Cn Ck equals to, I keep writing B, Cl plus Cm minus 2 CmCl. Now this one, I am familiar with from all the round 1 questions I've done. I can just try to factorize it. By completing the factorization, I'm going to sort of cheat a bit because I know what's going to happen. When I want to factor, I want to do grouping, but then if I group this together, that I want a factor of 2 here. So I'll multiply everything by negative 2 so that that factorization can come out more cleanly. But you could have just done completing the factorization straight away with the negative 2 there. It will also be fine. So what I've done here is nothing more than to multiply by negative 2. If I were to add 1, then this would come out. That allows me to do my last substitution. I mean, there's nothing much after this, is there? Oh yeah, I forgot. I wanted to say the range. So this one would be between 0 and 1. Now, if I times 2, it will be 0 to 2. I minus 1, it will be minus 1 to 1. So my range is negative 1 to 1. I've got dn dk equals to dm dl. This is the point where I remind you that the question also said that k plus n equals to m plus l. This is the condition that was there throughout the question. We haven't used it at all yet. It should be quite clear now what's going on, which is that this is a geometric progression. The easiest way to explain it would be that this is going to be dn over dm equals to dl over dk when n minus m equals to l minus k, right? This is this condition as well. And so in the case where n minus m and l minus k equals to 1, it gives you this, which is basically the meaning of a geometric progression. Now, in my opinion, at this point, if you have this and you just said that clearly it is a geometric progression, I'm fairly sure you will be fine. So just a quick, like, convincing ourselves more than really convincing the grader. You've come here, nobody's going to object to you saying it's clearly a GP. This is sort of like the integer version of your Cauchy functional equation. When it's in integers, you can always just by induction say it is true. And so therefore, it is a geometric progression that is stuck in this range. Now we are talking about boundedness as the objective for this whole question. A geometric progression has a common ratio that is either going to go up or go down. I mean, your sequence goes up or down based on whether the ratio is going to be big or small in magnitude. So if di is bounded, it means that the common ratio, at least the magnitude of the common ratio, is less than or equals to 1. In other words, it never really goes beyond the starting point in magnitude, right? It could go plus minus, but it cannot go beyond the starting point. So if I call D1, let's call D1 X. Have I used X anywhere? I don't think I've used X. So let's use X. Let D1 equals to X. In fact, no, let's let the absolute value of D1 be X. Then if the absolute value of D1 is X, then everything else is bounded below X. Right? And this is less than 1 because that's our starting point. So this is less than 1. This is less than or equals to X, which is less than 1. Which means that I have improved it from minus 1 to 1 to minus X to X, where X is strictly less than 1. Now I'm pretty happy. I can just U-turn back. So this is an improved bound. So C is D plus 1 over 2. B is 1 over C. Now you can tell that 1 minus X over 2 is strictly positive. That's good. Okay, and then finally, A is just B minus 1. And so this will be my bound, right? I was trying to establish that A is bounded, and I have done it. You can see that since X is less than 1, that means that this is going to be defined because X cannot be minus 1 or 1. You can also easily check that they are both going to be positive. And so they will be your B and C respectively in the original problem statement, which is what you wanted. You are, of course, allowed to show that it in terms of A1. So this is not for all possible sequences. This is a fixed sequence satisfying this. So if it's for all possible sequences, it's not true. You would be able to potentially say that my A's could go very, very close to 1. But, sorry, could go very close to 0. And so I can't put a fixed bound over all sequences. But for this sequence, I can let my bound be in terms of A1. So therefore, that is okay. And that concludes our discussion of what would be a return to normalcy for the senior round 2. This looks a bit more like the difficulty that we had in previous years pre-COVID. So new normal seems to have reverted back to the old, and I hope it was also kind of a nice feeling to be able to actually solve a non-trivial number of questions in round 2 compared to especially those of you who took senior last year. Final word on cutoffs, I do not have a clue. what kind of cutoffs there will be. Please let me know in the comments below. How did everyone do around you? If you were there today, was the mood better? Did more people solve more questions? Did anyone solve everything? I feel that definitely it is possible that at least a couple of students solved everything. And of course, if you would like to offer any suggestions about the solutions, let me know. Do refer to the link and the timestamp in the description below for the solution to question 2 in my junior review video. That's it. Thanks for watching. Have a good break, and if you're taking the open round 2 next week, all the best.